Hi everyone! Today, I'm excited to share a demo of our paper, One-Shot 3D Object Canonicalization, Geometric and Semantic Consistency. This work addresses the tricky issue of creating canonical 3D datasets. In 3D research, especially in generation and understanding, having canonical data is crucial. With canonical data, we see improved consistency and quality in 3D generation. However, we discovered that existing datasets aren't scalable. For example, ShapeNet has only 55 categories, and OmniObject 3D has just 6,000 canonical objects. On the other hand, there are tons of 3D object datasets online, like Objaverse, which contains 10 million items. The catch? Most of these datasets lack cleaning and canonicalization, making them difficult to use for training methods. Our analysis of Objaverse LVs revealed a long-tail distribution, where most categories have fewer than 100 objects. Trying to align these using previous algorithms poses significant challenges, especially since many require extensive prior knowledge. Plus, manual alignment can be a hassle. If you've used software like MeshLab, you know how tricky it is to move 3D objects around on a computer. To tackle this, we developed a one-shot alignment method. You only need to choose one reference object per category, allowing our approach to robustly canonicalize a diverse range of items. Based on this, we created the COD dataset, which boasts the largest number of canonical categories available. Our key insight is that alignment is closely tied to semantics. For example, when aligning a chair, we position its legs on the ground to establish the upright direction and set the back as the rear, completing the canonicalization process. To capture 3D semantics, we utilize a large 2D semantic segmentation model to extract the object's semantic information, projecting it into 3D. However, we found that existing 2D models don't perform well with every object. For instance, if you lay a chair down, it fails to segment properly. To solve this, we introduced an initialization strategy based on support surfaces to achieve accurate segmentation results. Using uniform or purely geometric constraints alone doesn't yield effective canonicalization. Geometry can get stuck in local minima, while semantics only provides a rough alignment. To address this, we propose a pipeline. For a new unseen object, we initialize it and get the semantic segmentation results. Then, by applying our combined semantic and geometric constraints, we generate numerous alignment hypotheses and select the best final alignment based on semantic relationships. We've tested our method on diverse datasets, achieving impressive results across simulation, high-quality reconstruction, and low-quality reconstruction scenarios, even aligning objects from Objaverse LVs with varying shapes and colors. Finally, we're excited to showcase our large-scale dataset, which is open source. Feel free to follow us for updates and join in the discussion. Thanks for listening.